we should be able to find those slopes. If I click on that line right there, maybe, come on. Okay, it gives me a slope of 3, that's AE, and then BD gives me a slope of negative 1/3. Okay, now what I want to do is I want to actually go through and figure out how can we algebraically show that those are really the slopes. Okay, so when we want to find the slope of AE, and we want to find the slope of BD. Remember, what is your slope formula? Good. Slope is y2 minus y1 over x2 minus x1. Okay? I think it's probably beneficial for you guys to also see different ways that they write formulas. Slope is delta y over delta x. You might see it that way, where delta y just means change in your y value, and change algebraically means subtraction, okay, or difference. I think it's really important for you guys when you start to be introduced to formulas, and we have 3, 4, 5 different ways of writing the exact same formula, that you expose yourself to all of them. I've got some students in algebra, college algebra, trigonometry class that are in physics, and they're working with some formulas that they learned in geometry. Okay, they learned their formulas for sine, cosine, and tangent, but they're written a little bit differently in physics. And if they can make a distinction that this physics formula is exactly what I learned when I was in the 9th or 10th grade in geometry class, it makes the physics so much easier. Does that make sense? So same kind of concept. Learn the different formats, so it'll make your life a little bit easier later on. Control Z will select that, or sorry, Control A selects everything, and then delete will clear. So I'll find a slope of AE. Now I need to use the points that exist on AE, and you can use any set of points that you want to that exist on AE. Okay, if I take that point there and that point there, okay, let's just kind of convince you of this. All right, so moving C and F around, we get that idea that slope between those 2 points is always 3. So you have the option when you're doing this in your homework and they ask you to find the slope. It doesn't matter which point you choose off of AE. You can choose the points that I currently have as C and F. Okay. My only suggestion is, and my thought is, and this is why I wanted to demonstrate this, is it really going to be easy for you to take C and F where they're currently located and know exactly, and this is out to 15 decimal places, but GeoGebra is using much longer decimal places. You're using an infinite number of places. Is it going to be really easy for you to know that C is at an X value of 4.087840086589158? No. Okay, you have to kind of guess, right? So when I need to choose, because I'm going to do things by hand, when I need to choose the slope or determine the slope by choosing particular coordinates, it makes sense to use coordinates that I either know because they've told me exactly what they are, or they're coordinates that pass through grid lines, the intersection of grid lines. So you see where I put C right there. It kind of snapped it to those grid lines, right? And it made C at 4, 3, right? So it might make sense to use 4, 3, and maybe I come down and F would be, maybe I choose that point there where E was, okay? So 2, -3, okay? But hopefully, logically, you guys say, well, why not just use both endpoints, right? But my hope is that you recognize, because you might see this type of problem on your in-course exam, where you have to find the slope of some type of segment, and you have choices of points to choose. Choose points that you know for certain are intersecting at grid lines. Okay, and in this case, the endpoints, because they were integers, are doing this. That's what we're going to use. Okay, does that kind of make sense, everyone? All right. So find the slope of AE. I think the best thing to do would use points A and points E. Okay, A is located at 5, 6. E is located at 2, -3. So I'm going to go up top, y2 minus y1, so 6 minus -3. And on the bottom, x2 minus x1, so 5 minus 2. And that gives me 6 minus -3, which becomes 9, right? And then 5 minus 2 becomes 3. And the nice thing about using GeoGebra already is that I knew I should have gotten 3, right? And that is the work that proves that. Here's my thought for you. I did subtraction 6 minus -3, right? What if I did -3 minus 6? -3 minus 6. Then on the bottom, I gotta go 2 minus 5, right? What's -3 minus 6? If you owe somebody $3 and borrow 6 from them, you owe them 9, right? So you're $9 in the hole. What's 2 minus 5? -3, right? What's a negative divided by a negative? Positive. So it does not matter. The slope formula does not know what x1, y1, x2, y2 are. Is x1, y1 A, or is it E? And it doesn't matter, because if I go from A to E, the slope should still be 3. And if we go from E to A, the slope should still be 3, right? Okay, it's the same exact line. So that order doesn't matter. Okay. However, you cannot flip them. If I went -3 minus 6 on the bottom, I cannot go 5 minus 2. Because that would give me like y2 minus y1 over x1 minus x2. And that's going to mess up signs. I'll have the numerical, I'll still get 3, but it won't be positive 3, it'll be -3. And that's an issue. Okay, so my slope going in the wrong direction. The next thing we want to do is find BD. So B was at -1, 3, and D is at 8, 0. So again, the difference in Y is 3 minus 0, and then the difference in X is -1 minus 8. So it gives me 3 over -9, gives me -1/3, right? So the question was, graph those points, label point C, find the slope. Part B says find slope. And now it says, how could you describe angle ACB and angle ECD? Well, if I look at what we just found, okay, this point here is C, right? And what we just found is that the blue line and the, you guys see that orange? Is that okay? Let's do it that orange. The blue line and the orange line are what to one another if they have opposite signs reciprocals for the slopes? They're perpendicular. Okay? So we got right angles. So those are right triangles, correct? Okay? That's what they were trying to get at here. The next thing is, can we actually find that ordered pair for C? Okay? And when I put C there, I think that's intersecting. It looks like, 3.49, 1.48. Maybe that's what I guessed. Okay? Most people probably would have guessed 3.5, 1.5, right? Okay? Let's see if we can go through the algebra to convince ourselves of that. Okay? And that's the next task, is to find the coordinates of C. Okay, this is part C. But in order to do that, we need to do that first part of C. It says write equations of AE and BD. And this is where I told you yesterday, if you forget a little bit of your algebra from last year, go back and watch the videos that I posted, and it should walk you through this. Okay? I'm going to just kind of over here write down what my slopes were and then erase everything. So this was 3 and this was -1/3, right? If you watch that video or series of videos yesterday, I talked about finding the equation of a line. Every line that you ever come across is going to be of the form of y minus y1 equals m referring to the slope of that particular line, times x minus x1. Does that make sense? What I need you guys to understand, because this is an issue that people have all the time, that y and that x are static. They don't change. You don't insert them with other values. Okay? But the y1 and the x1, they can be anything that comes off of the line that you're trying to find the equation for. So let's say I'm looking for AE. Okay, we're trying to find the equation of A to E, this blue line. Okay? I need to, one, know the slope of it, which we've done the work for. Okay, we know that's 3. And I also need a point that I know for certain is on that line, right? Okay? So it's probably a good idea to use points that graphically intersect at grid lines, right? It would make sense to use, you know, maybe that point right there, because that's an intersection of grid lines, right? Maybe it would make sense to use that point there, because that's an intersection of grid lines. Does it make sense to use that point right there, C? No, because I got to kind of guess, right? I got to kind of guess. That's 4.6-ish, comma 4.7-ish. Okay, well, that's not very accurate. It will give me a line eventually that's pretty close to AE, modeled AE pretty close, but it's not exactly AE. So you want to use points that you know are exact points. And most of the time, right now, you're looking for integer values. Okay? So we need a point that is off of AE. So from our problem, we know A is a point that is on AE, right, on that segment. And E is also a point that is on that segment. So when I start plugging stuff into this formula, Y stays Y. Now Y1 comes from one of these ordered pairs. Okay? So let's just use A. We'll go 5, 6. Okay? So Y1 is the Y value that came from A. So I'll put 6. My slope M, we said, was 3. X is always X. And then x1 is the x coordinate that came from the point that I chose. So 5. At this stage, all you do is you solve for y. So I get y minus 6. Do a little distributing here. 3x minus 15. Add 6 to both sides. I get 3x, minus 9? Okay? Now I want to prove to you that it doesn't matter what point you have chosen. If I chose E, E is on AE, so I go 2, negative 3. And I'll go y minus y1, so now negative 3. So y minus negative 3 becomes y plus 3. Slope is still 3, but now it's x minus x1. x1 is 2. So we get y plus 3 equals, now distribute 3x minus 6. Subtract 3 to solve for y. Do I get 3x minus 9? Same equation, right? So hopefully that's visual proof for you that it doesn't matter what point you choose off of your line to use as x1 and y1. But now I know AE's equation is y equals 3x minus 9. Now I want to do the exact same thing, but it wants it for BD. So for BD, be intelligent. You know you're going to have to, the BD line is going to force us to plug in a y minus y1 equals m times x minus x1. What is maybe one of the easiest numbers that we ever have to do? If I want to add something or I want to multiply by something, what is the easiest number to add to anything or the easiest number to multiply by anything? 0. 1 is awesome. 1 works. 1 is really easy, but 0 is even easier. Okay? So if I have an option of an ordered pair on my line BD that has a 0 in it, I'm going to use that one. Okay? So I'm going to use 8, 0. Because now I got y minus y1, y1 being 0. M is negative 1/3. And then x is 8, right? So then I get y minus 0, that's just y. And then negative 1/3 x plus 8/3. And there's my equation for BD. All right. Using that 0 saved a step for me, right? I didn't have to isolate y. It was already kind of built into the use of that point. Is that doable for everyone? All right. Now, what I like about GeoGebra because I know that maybe we struggle sometimes with that process. If I've got this thing graphed, okay, we can actually, now you have to make a line here. But if I come to my line tool and I click on A and E, hit enter, it gives me this. Now, I got to do maybe a little bit of work here. That's in what we call standard form. If I right-click on that equation, put it into y equals mx plus b form, and there's the 3x minus 9 that we found, right? If I click on B to D, do the same thing now with that, put in y equals mx plus b, now it puts it in fraction form, negative 1/3 x, okay? And then 2.666666 repeating is that 8/3 that we found. Does that kind of make sense? So you can use GeoGebra to maybe verify that you've done everything right algebraically. The next thing they ask you to do is to now find the coordinates of C. And my hope is that we do this algebraically. We don't cheat. Okay? And what I mean by cheat, if I look at my graph over here, cheating would be, 3.5 is what it looks like, up 1.5, right? But we've always talked about how maybe it's really at 3.4 or 3.45 or 3.49. And your eyes can't tell that, right? The algebra should tell us exactly what we need to do, okay? Or the exact ordered pair without any guessing. And we're going to use these two lines. If you remember back to Algebra 1, when we talked about systems of equations, and all the work that we do with substitution, elimination, the graphical concept is that you are finding the x and y coordinates of where two lines intersect. So if that's what I'm trying to do, I'm trying to find where two lines intersect, and it must be systems of equations that allow me to do that, allow me to get to that answer. So if I look at those two equations, do they have the same two variables? X and y, right? That's a system. All right. Now, it's a system that's actually pretty easy to solve at this stage, because if you know that these two things are y, and they should be the same then, right? So what's that tell you about these two things that are yellow? They're the same. So I'm going to write 3x minus 9 is equal to negative 1/3 x plus 8/3. Okay? Now, that's an ugly equation because of the fractions, right? What can I do to get rid of those fractions? Multiply everything by 3. The reciprocal, yeah, I could. And my suggestion is just look at that denominator, the least common denominator, multiply it by it. Okay. You could multiply everything by 3/8 or 1/3, and it's just going to be a little bit bigger coefficients that you need, but it will get rid of fractions. But whatever that common denominator is, multiply by that. So 3 times 3x is 9x. 3 times negative 9 is negative 27. 3 times negative 1/3 gives me negative 1. And then 3 times 8/3 gives me 8. Is that equation a little bit easier to solve? Add x to both sides. Add 27 to both sides. So that's going to give me, what, 35? And now divide by 10. Okay, so 35 over 10. Both those have 5 to go into them, right? So 5 goes in there 7 times, goes in there 2 times. So x is 7/2, right? Okay. X is 7/2. Now, I'm going to leave it as 7/2 because of what we might do later with that number. It's a lot better as 7/2 than it is as 3.5. Okay. I'm going to come over here. I'm going to plug that in to this top equation to find y. That top equation makes more sense than the bottom one because the bottom one has fractions, right? I could use the bottom one, it'll work. Top one's a little bit easier. So I'll say y is equal to now 3 times 7/2, and then minus 9. Okay? 3 times 7/2, that's 3 over 1 times 7 over 2. Take numerator times numerator, and then denominator times denominator. Which gives you 2, right? Minus then 9. Well, to subtract fractions, I need a common denominator, right? So is 9 the same thing as 18 over 2? So now what's 21 minus 18? 3. So you get 3 over 2. So my x value was 7/2, and my y value is 3/2. And that's exactly what we would find out if I go to GeoGebra, click on the point tool, come down to where it says intersect, click on the two segments that I'm interested in intersecting. It gives me point G, and if I look at G down here, its coordinates are 3.5, comma 1.5. 7/2, comma 3/2. Okay? So, that's the algebra to do part C. Okay? Now, we actually have to go through and find these distances, and we've dealt a lot with distances so far. But we need that point that we just came up with of C to come up with all these distances. So I'm just gonna write these things real quick. A was 5, 6. B was -1, 3. D is 8, 0. E 2, -3, and C was 7/2, 3/2. Okay, and they want us to find the distance for AB, BD, AB, BC, DC, and DE. Remember, distance between 2 points is this formula: x2 minus x1 squared plus y2 minus y1 squared. Hopes are that we also know that could be rewritten this way: delta x squared plus delta y squared, knowing delta x means that right there, and delta y means that right there. Okay? So let's find the distance between A and B. Subtract your x's. What's 5 minus -1? 6 squared? 36. What's the difference between 6 and 3? 3 squared is 9. So I get radical 45, right? I'm going to leave it right there like that. We need to simplify that here in a little bit, but we'll do all that simplification later. Let's go find distance between B. Let's do DE first. DE will be a little bit easier. Find the distance between D and E.
4.
So 8 minus 2 gives me 8 minus 2. 6. Square that. 36. 0 minus -3. Squared is 9, right? And that gives me a radical 45, correct? What's that tell me about those two distances?
0.
Careful. It just tells me those two distances are equal, right? I haven't put it in a picture yet to determine whether I use isosceles or not. Now we're going to go find BC. And then the reason I say this for last is because of the fractions. If I'm going to subtract these two things, okay, and then square, okay, it is so much easier mental math-wise to do this with fractions, okay? If I ask you to take 2.5 and square it, does anybody know what 2.5 times 2.5 in their head is? It's taking your time, right? If I tell you that 2.5 is 5 over 2, correct? And I ask you to square 5 over 2. What's 5 squared? 25. What's 2 squared? 4. So you get 25 fourths, right? That's something you can do in your head a lot quicker than 2.5 times 2.5. So, in working with fractions, it might be logical here to turn point B into a point that has the exact same denominator that this one has, but not change its location. So would you agree that -2 over 2 is still a -1 here? And it has the same denominator that this had, right? And then 3 would be 6 over 2, wouldn't it? And that's the same denominator that this one has. So now it's going to make things a little bit easier. What's -2 minus 7? Yeah, -9, right? Okay. -9 squared is 81. Okay. Now, hold on a second. So we did -2 minus 7 gave me -9 squared. That gave me 81. Now I got to do the denominators. Okay, when I subtract fractions, the denominators just stay, right? They stay the same. So what's 2 squared? 4, right? So that 81 over 4, just kind of writing this down, we just did negative 2 over 2 minus 7 over 2, and that gives me negative 9 over 2, right? When you take negative 9 over 2 and you square that, I got 81 fourths. So hopefully that shows you then that when you have a fraction, you want to square it, your laws of exponents say square the top number, square the bottom number. That's all you got to do. Does that make sense? Okay. Now let's do the y's. If I take 6 over 2 and subtract from it 3 over 2, right? What's 6 minus 3? 3. Denominator stay 2, right? Square that number. What's it going to give you? 9 fourths. Okay? So when I add those together, I get, what's 81 plus 9? 90. So we get 90 over 4, right? Okay? Now we also wanted to do, and we'll do this a little bit quicker, but we want to find DC. So DC. Now again, D probably makes sense to make that 16 over 2 and 0. Okay, so I go 16 over 2. 16 over 2 minus 7 over 2 gives me what? Gives me 9 over 2, doesn't it? We'll square that. Okay, and then I go 0 minus 3 halves, just give me negative 3 halves, or positive 3 halves, and I'll square that. And again, what's 9 squared? Or sorry, 9 over 2 squared is 81 over 4 again, right? 3 over 2 squared is 9 over 4 again. Is that going to give me a radical 90 over 4 again? Okay, so I know it's a lot of work here, but A, B, and D, E, which in GeoGebra, that point there is C. So A, B, did I write that right? A, B, and D, E. So we've got some things messed up here with the coordinates. Let's go back to A, B, D, and E. D, and E. Did I find the right, did I label them right? Doing an A, B, B, C, and it doesn't really change much of what we've done, but I think my triangles I had should have been like that. Okay, still gives me the correct things. Okay, the correct, all the same slopes and all that kind of stuff. And I'm going to actually go back to the last picture, but this is really what they're looking for. But we just found out basically that through the work, that distance are the same. Right angle there, and that distance are the same, right? So what they're trying to show us then, or ask us, is what types of triangles are those? In the hopes you say the right triangles, right? And then what conclusion can you make about them? The conclusion should be that they're congruent, correct? But by what property? What theorem? See him? Hypotenuse length. Good. Okay. The last part, and you probably would have answered this before you actually got to justifying that statement there, is how to simplify these things. Okay? And let's just look at radical 45 first. And this is algebra, so if you haven't been paying attention yet, please listen, because of how much you're going to use radicals in the coming weeks and months, and we'll be to a point where you think that every single number we use is a radical. Okay? That's how much we'll use them. And we're not going to use our calculator to change them into decimals and that kind of stuff. We're going to focus on the algebra of how to simplify these. There's a couple different approaches, okay? And what kind of What I don't like about math is a lot of times that you may learn procedures or what we call algorithms to go step by step to get a solution or a simplified version of something, but not really have enough math yet to understand why that works. Okay? You guys, I don't know if, how much you talked about law of exponents in Mrs. Cole's class last year. I know you did talk about them. But what we do here in a moment is going to use law of exponents. Okay, so we don't have time to really get into it in depth, but kind of show you some procedures here. My hopes are that you don't use the long procedure very, very often. Okay, basically what we're trying to do, radical 45 is a symbol for another number. It's a symbol for some number that I multiply by itself twice to get 45. Okay, so if you think about that, it's probably somewhere between 6 and 7, right? The 6 times 6 gives me 36. 7 times 7 gives me 49, right? So 45 has to be the number that I multiply by itself. 2 times you get 45 is going to be somewhere in between 6 and 7. So it's a symbol. And the way we simplify this symbol, to get it in a different version, is to think about the largest perfect square that will evenly divide that. Okay? What I mean evenly is that when I divide it by something, I get a quotient that is a whole number. Okay? No remainders, no decimal parts. So if you think about that concept, okay, this is called number theory. This idea or logic is the only way that I can divide that and get a whole number back. The smallest whole number I get back would be 2. Does that make sense? You can divide it by itself and get 1, but that's not really interesting. If I divide it by something, the first whole number that I would get back could be 2. So what do I have to take 45 and divide it by to get 2? Yeah, what if I give you any number? Let's say I give you 100. What would you have to divide 100 by so that you get 2? 50. And 50 was what of 100? Half. Okay? If I gave you 200, you would divide by 100 to get 2, right? Take the half. Okay? So I'm going to look at 45 and divide it into 2. Okay? Now it doesn't give me a real nice number, but it gives me 22 and a half, right? So I start thinking now, okay, if I'm looking for the biggest prime number that will divide 45 and give me a whole number back, it has to be a perfect square that is less than 22 and a half. Okay? Does that make sense? And this is useful. This process is useful when that number becomes really big. That number is like 450. It'd be a lot easier, instead of looking at all the perfect squares that are less than 450, it'd be a lot easier to look at all the perfect squares that are less than 2.5. Okay? So, 22.5, the perfect squares that are less than that are 4, 9, 16, right? Does that divide by 4, 9, or 16? Divides by 9, right? Okay? So when you take 45 and divide it by 9, what's that give you? 5. So what that tells me right now is that 45, the best way to factor that would be 9 times 5. Okay? Now you also know from laws of exponents from last year that this is radical 9 times radical 5. We don't have time to get into why you can do that. If you have a product of radicals underneath, a product underneath a radical, you can change that to a product of radicals. And now what is the square root of 9? 3. So we get 3 radical 5 is the simplified version of radical 45. Last year you probably learned this technique. Take 45, divide it by just some factor. Maybe you divide it by 5. And then you take and get 9, right? Well, that information right there is what we got there. But then you said, well, 9 can still divide. And you divide that by its factors. So what we just determined there is that radical 45 is actually the same thing as radical 5 times radical 3 times radical 3. But when you multiply two numbers together like that, if I give you just 3 times 3, how could you rewrite that with exponents? If I give you 3 times 3, you write it as 3 squared, right? Okay. Well, if I've got radical 3 times radical 3, how are you going to rewrite that with exponents? Radical 3 squared, correct? So we're going to go and write this as radical 5 times radical 3 squared. Okay, now think about what happens here. If I take radical 3, it gives me this big ugly number. Okay? And then I square that big ugly number. What do I get back to? Just 3. What that tells me is that those are inverse operations. They undo each other. So square root and a power of 2 cancel each other out. And I'm left with radical 5 times 3, which we always put that, we call that a rational number. We always put that out front. So it's 3 radical 5. And that's how you simplify that radical. Okay? I'm going to let you go to lunch here. But we can finish, and I will finish here, how I would simplify that 90 over 4. Okay? So I'll add that to the video. I want you guys. Okay, so the logic behind simplifying radical 90 over 4 then is very similar to what we said when we did radical 45 was equal to 9 times 5, and we could break that up to radical 9 times radical 5. Okay, when you end up with multiplying, you have a product underneath your radicand, you can break it up into a product of radicals. Well, when I have a quotient underneath, I can break that up into radical 90 divided by radical 4. Okay, so when you have a fraction underneath the radical, go ahead and just, I said quotient, but the word I wanted was ratio. When you have a ratio underneath the radical, you can break that up into 2 radicals. And this all has to do with what we know about laws of exponents. Kind of maybe a side note here. Why does this work, or why does that thing there work? You guys should have learned last year that if I have a to the m, let's just do it this way, a squared times b cubed, and you raise that to the 4th power, you could rewrite that as a to the 2 times 4. So you take that exponent, multiply it by that one, and then you take it as b raised to the 3 times 4. So it gives you a to the 8th times b to the 12th. Okay. The generic rule for that is if I have a raised to some m and b raised to some n, and then I have maybe some s out here, then that gives me a to the ms times b to the ns. Okay, and showing that multiplication. Well, what you don't know is that a radical is actually an exponent. Okay, and we write this as 45 to the 1/2. The square root is a 1/2 exponent. If you want to convince yourself of that, you can go to a calculator and type in 9 to the 0.5. You should get the same thing as the square root of 9. You can take 16 raised to the 1/2, and you should get the same thing as the square root of 16. But where does this kind of lead us to this is that we can say that, well, 45 is the same thing as 9 times 5, still raised to the 1/2. These 9s, that 9 has an exponent of 1, that one has an exponent of 1. We can use that rule that said a to the m times b to the n raised to the s is equal to a to the ms, b to the ns. So basically say, take that exponent and multiply it by that 1, so I get 9 to the 1/2, and take that exponent, multiply it by that 1, and I get 5 to the 1/2. But now working our way backwards, if that was the same thing as radical 45, then this thing better be the same as radical 9. And then this thing is the same thing as radical 5. So that is all the math. I know that's a lot, but that is all the math that allows me to go from radical 45 straight to saying radical 9 times radical 5. Same thing happens with division here. When we have division, we have the rule is like if I have, we did this one in class, but if I have like 2/3 and raise that to the 2nd power, we square the top and we square the bottom. All right, well, if this was a 3 there and this was a 4 there, we'd actually take 3 times 2 as that numerator and 4 times 2 as that numerator. So that rule is very similar to the other one where we have a to the m over b to the n raised to the s eventually gives me a to the ms over b to the ns. Well, if a radical, again, is just the fraction of 1/2, okay, I'm going to rewrite this as 90 to the 1/2, 4 to the 1/2, and then know that 1/2 is the same thing as a radical or square root. So I have radical 90 or root 90 over root 4. So that allows me to go straight from here to that. Okay, and that's the thing about mathematics, is that there's, you know, very simple things that you've been taught early on that is pretty complex, and why we can make just a simple transition from this statement to that statement. But now, once I get this, now this radical 90 is simply trying to think about what is the largest perfect square that divides 90. I see 90 and I think 9 right away. May or may not be the largest perfect square, but I know it's a perfect square. So I can take 90 and rewrite it as radical 9 times radical 10. I see radical 4, and I know that that's 2. Now you start simplifying. Radical 9 is 3. Radical 10 is just radical 10 over 2. I just want to make sure that that number right there is simplified. So what I do is I say, okay, are there any numbers that divide 10 evenly that are perfect squares? And then the only way I have to do that is I look at 10, I take half of it, so that's 5. And now I think about the perfect squares that are less than 5 that could divide 10. Perfect squares that are less than 5 are plus or minus 1 or plus or minus 4. And we know that if we divide 10 by either of those, or sorry, divide 5 by either of those, we're not going to get a whole number back. Okay, so we're not 5. We want to divide 10 by either of those, but we're not going to get a whole number back. Okay, when I cut this number in half there, or maybe when I cut this one in half in class, that tells me the perfect squares to try. We try the perfect squares that are below that number and see if they divide 45 evenly, or in this case, divide 10 evenly. So 3 radical 10 over 2 is our final answer, and that's how we would type that into MathXL.